Everyone, welcome back to my channel Ankur Education. I would like to thank the subscribers who subscribed my channel and thank you for your support and encouragement and keep watching my channel. Now let us enter into a session. Today's topic is about the types of currents. In a semiconductor, there exist two types of currents. One is the drift current and the other one is the diffusion current. In this session, we are going to discuss about these currents in detail. First of all, let us go to drift current. What is meant by drift current? The definition of drift current is the current which is due to the drifting of carriers. That is the definition for drift current is the current which is due to the drifting of carriers under the influence of applied electric field. Under the applied electric field, say epsilon. So, is called as the drift current. So, we can write the definition as the current which is due to drifting of carriers by the applied electric field is called as the drift current. Within a semiconductor, intrinsic or impure, because of the thermal energy, covalent bonds are broken and electrons and holes move in random motion. These collide with lattices, get deflected and move in different direction till they collide with another carrier. Such a random motion is defined by the mean free path length L, the distance a carrier travels between the collisions, and the time taken between the collisions is denoted by T. So, the average velocity of motion V is equal to L by T over a period of time which is far greater than T. The average movement or the net current is 0. That is, the I net is considered to be 0 over a period of time for T for large values. But when electric field is applied, all the electrons are aligned in a particular direction and move towards the positive electrode and holes in the opposite direction. The resulting current is known as the drift current. So, we can say that the movement of holes and electrons will move to either positive side or positive electrode side or negative electrode side. Due to the movement, we get the current called as the drift current. We can explain this by using a diagram as shown in this figure. Here the concept of drift current can be explained with the help of the following diagram. Here we are taking two electrodes. One is a positive electrode and negative electrode, and this is a battery, and the semiconductor used here is assumed to be N-type. So, now using a battery, electric field is applied. Under the influence of this electric field, all the electrons will move towards the positive electrode side. That means because of the applied electric field, the electrons move towards the positive electrode side as shown in this figure. The donor atoms have thus lost their free electrons. Such the donor atoms near the positive electrode will pull the electrons from the electrode. That means here the donor atom, that is the N-type, will pull the electrons from the electrode. So, the semiconductors remain electrically neutral. That means first of all the electrons will be moved towards the positive electrodes. Because of the donor type, that is the N-type, the electrons will be moved towards that means pulled out from the positive electrode. So, the semiconductor remains electrically neutral. The voltage applied results in voltage drop across this semiconductor. There exists a voltage drop across this semiconductor. If the battery is removed, here if there is no battery suppose, then the number of free electrons and holes is same as before the application of field, since the semiconductor has taken equal number of electrons from positive electrode. So, when the free electron contributed by say phosphorus, that is of N-type, donor atom goes into the positive electrode, the donor atom loses one electron. That means the phosphorus will lose an electron. Therefore, it will pull one more electron from positive electrode, and hence the number of free electrons in the semiconductors remains the same. Here we can see the give and take policy. That means first it gives out the electron and then it takes the electron from the positive electron. In this way, the drift current is generated in N-type semiconductor, and the process of drift current in P-type semiconductor is similar to the N-type, except here the electrons will be moved towards the negative electrode side instead of positive electrode side in p-type semiconductor. So in this way we can find out the drift current in n-type and p-type semiconductor. And the expression for the drift current in semiconductor, we can write it as I drift is equal to J drift into A. This is the modified version of basic formula I is equal to J into A. So here the drift current density J is equal to N mu N plus P mu P into mu epsilon Q epsilon into A. This is the expression for drift current in semiconductor. This is very important to remember. Let us take this as equation number 1. Now let us discuss about the diffusion current. As by definition, it is a current which is due to concentration difference. That is, the current due to concentration difference is called as the diffusion current. Concentration difference. Here there is no applied electric field, that means no epsilon is present here. That means the diffusion current is independent of applied electric field. Because of concentration difference, carriers are moving from one place to another place. That is, the free electrons and holes are not uniformly distributed all over the semiconductor. In one particular area, the number of free electrons may be more, and in some other area it will be less. So the electrons where the concentration gradient or the concentration of carriers is more will move from that region to the place where the carriers are less. This is true with holes also. So let us draw a graph that is showing this concept. Let the concentration of some carriers be as shown in this figure. That is the graph between conductance and distance of along the semiconductor. That means here we are showing a graph between the conductance and distance of the semiconductor. The carriers is not uniform and varies as shown along the semiconductor length. Here we are assuming that the area A1 is greater than the area A2. That means area A1 is a measure of the number of carriers between x1 and x2, and A2 is the number of carriers between x2 and x3. Here we are considering two areas and we are assuming that A1 is greater than A2. That means the number of carriers in area A1 is greater than number of carriers in area A2. Therefore, they will move from A1 to A2 because the number of carriers are less in A2. They will move from A1 to A2. If these charge carriers are free electrons, suppose the carriers are electrons, then the direction of current, that is the current direction, is from C to A. If the charge carriers are holes, then the current direction is from A to C. This current is called as the diffusion current. It is independent of applied electric field epsilon. So in semiconductor, at room temperature itself, though there is no electric field applied, this is a very important point to remember. If the device is connected in a circuit, there will be very small current flowing through, which is called as the diffusion current. So we can write it as this is independent of epsilon, that is the independent of applied electric field epsilon. So if there is no electric field also, there exists a very small leakage current which is known as the diffusion current, and it is denoted by I diffusion. So we can say that the diffusion current is due to the concentration difference of carriers between the two areas. We can write the expression for JP diffusion, that is the diffusion current in p-type semiconductor, that is due to holes. Diffusion current due to holes is proportional to minus dP by dx. Similarly, we can write the diffusion current due to electrons is given by Jn diff proportional to dN by dx. Here we are taking the negative sign because it is in opposite direction. Here for electrons we are not considering the negative sign because it is in the same direction along the length. And if we remove the proportionality constant, we get the expression for JP diffusion as minus q dp into dp by dx. Similarly, Jn diff is equal to, that is the diffusion current due to electrons is given by, current density due to electrons is given by Jn diff is equal to q dn into dn by dx. So this is the current density, and here the dn and dp are called as the diffusion constants of electrons and holes. Diffusion constants of holes and electrons respectively. The values of dp and dn for silicon and germanium are predetermined. So the value of dp is equal to 47 centimeter square per silicon per second for germanium, and its value is 14 centimeter square per second for silicon. Similarly, the dn value for germanium is given by 99 centimeter square per second, and for silicon it is 34 centimeter square per second. Hence, we can write the expression for diffusion current I diffusion is equal to q dn by dx minus q dp by dx into A. So, since I is equal to j into A, we are writing it as q dn into dn by dx minus q dp into dp by dx. This is a very important expression for finding the diffusion current, and these expressions are very important in solving the problems as well as in objective type questions. So the total current is a sum of the drift current and the diffusion current. So I is equal to I drift plus I diffusion. Let us take this as equation number 2. This is the total current. Hence, from equations 1 and 2, we will get the total current as I is equal to N mu N plus P mu P into Q epsilon plus Q dn into dn by dx minus Q dp into dp by dx, and hold this into A. So this is a expression for total current in semiconductor. This is very important to remember. Hence, the total current is a sum of the drift current and the diffusion current, and the drift current is due to the drifting of carriers under the influence of applied electric field, whereas the diffusion current is due to the changing in the concentration levels of carriers between two particular areas. That is known as the diffusion current, and the total current is sum of these two. Hence, in this lesson, I try to explain about the types of currents in a semiconductor. I will continue my topic in next session, so please keep watching my channel, and if you like my video, please do like, share and subscribe to my channel. Thank you for watching my video, and once again thank you for all the new subscribers. Thank you.